let's get down to it. So today I want to talk about NFA versus DFA. What I mean by that is what precisely are the capabilities of NFA as compared to DFAs. All right. So we already know that DFAs can generate, I will say, any regular language, right? That's actually the definition of what a regular language is. All right? And NFA have some extra capabilities, right? They can do epsilon transitions. They also can, the diagrams can be weirder in the sense that they may have extra arrows. They may have not as many arrows. So NFAs, if anything, maybe are capable of some more stuff than DFAs because they are allowed to do different things, more things than DFAs. DFAs can generate any regular language. I want to say, what about NFA? All right. And the answer is, like, if anything, the NFAs can do more than the DFAs, right? Because they have more capabilities. And in fact, it is true that, yeah.
Our DFAs contain this, right?
Yeah, right. That's what I was about to say. Every DFA is already an NFA, right? You can just consider it to be an NFA which doesn't have any epsilons and doesn't have extra hours or whatever. So I will say any DFA already counts as an NFA. NFA. All right. So that automatically means that every regular language, you can do it with an NFA because you just use the DFA and call it an NFA instead. So any regular language can be generated by an NFA. Right? That's just because every DFA is also an NFA. So any regular language can be generated by an NFA. But, so the interesting question is, are there some languages which an NFA can do but not a DFA? Right? Are there some languages that you can do with an NFA but you cannot do those with a DFA? And we're going to, so I will say, can NFAs do any non-regular languages? That's the interesting question. And, I'm going to close the door. I'm going to spoil the answer a little bit. The answer actually is no. Oh, sorry. The answer is no. NFAs actually, this is maybe a bit surprising. I know this is surprising when I learned this first. NFAs actually have the same capabilities as DFAs, even though they can, like, structurally as a machine, it can have more general things. It can have the epsilons and whatever. But actually, when you add that all up, they actually don't have any languages which you can do with an NFA but not a DFA. So the answer here is no. And the way that we're going to demonstrate that, actually, there is a procedure that's vaguely like this sort of the unions and intersections with the products machines. There is a procedure to convert any NFA into an equivalent DFA. All right. This means actually, like, from the point of view of the theory of computation about different kinds of machines and their capabilities, NFA and DFA are actually the same kind of thing. They have, like, slightly different descriptions, but the kinds of things they're capable of computing are the same, and they are the regular languages. All right. There's a procedure to convert any NFA into an equivalent DFA. That means anything that you could do with an NFA, you can also do with a DFA. Usually the DFA that you get will be bigger than the NFA that you started with. Yeah.
Are all non-regular languages equal?
Yes.
They cannot be into finite automata because they are even instance.
that's not really why. He asked the question, are all non-regular languages infinite? And the answer is yes. Remember, a language is just a set. If your language is ever a finite set, then you can make then you can make a NFA or a DFA to accept it. If it's only a finite set, by just basically checking all the finitely many elements of the language. But there are many infinite languages which are still, like actually almost all the languages we've ever talked about are infinite. Like, something like a to the n where n is even. This.
I mean, the set of states are infinite.
Okay, the set of states are infinite. Yeah, you could imagine something like a DFA or NFA which allows infinitely many states. That actually is not something that we're going to talk about this semester, and I think that is not. I think people tend not to talk about that because that doesn't actually correspond to machines that you can build in reality, because a real life machine cannot have infinitely many possible states. Yeah, these are all good questions. Anyway, I want to talk about this procedure. That's kind of our main goal for the day. I show you an NFA, and you can convert it into a DFA. For example, this we're not going to work out, but for example, this is an NFA. Let's see if we can think this through about what is accepted here. This is an NFA, and it accepts. Can anybody say what is the language accepted by this one? I don't know how used you are. Are you used to reading NFA diagrams? What do you think?
A to the power n.
Yeah. And
B to the power n.
yeah, so this will accept any string that looks like this. It has some power of A's followed by some power of B's, where the n and m, I'll say n and m are natural numbers. Right? You can go up here and do the A a bunch of times. So this gives you a bunch of A's, and then if you want to, you can go down here and do a bunch of B's, and that's it. From there, you can't go back to do more A's. All right? Yeah, this accepts A to the n, B to the m. That's an NFA, but this language also you can do with a DFA. This is less obvious, but I worked this out ahead of time. Here is a DFA which does the same thing. I have a starting state which does like that, and then so here you can see I start somewhere, the empty string is accepted, and then if you want you can do a bunch of A's over here, and then this is a B, and then you can come over here and do a bunch of B's over here. If you do another A after that, then this is rejecting. All the other ones are accepting. And then we also need, from the starting state, you could immediately do B's like that. All right? So this is a DFA, which is equivalent to that one. This is an equivalent DFA. And actually, the procedure, I said we're going to talk about a procedure to convert an NFA into a DFA. Actually, the procedure we're going to talk about today will produce the second diagram if you start with the first one and you do this thing, which we're about to do. You will get the second one over there. This is a general purpose procedure to convert any NFA into an equivalent DFA. All right? And it's not, you can tell in this example, the answer is not really going to look like the first one. It might have a different number of states. It certainly is going to be a DFA, so it cannot use epsilon, so there will be quite different. Yeah, so that's what we're going to do. So I want to try and describe this. It's called, our book refers to this as the subset construction. All right, we've already had the product construction, is where you take two DFAs and you combine them by the states in the product construction are products. They're pairs of states from the original two things. The subset construction is each state In our DFA, that's the result. You know, remember the setup is we're going to start with the NFA, try to convert it into a DFA. And each state in our DFA will be a subset of states from the NFA. All right. So I'm going to try and actually do it on that example that I wrote up there. I'm going to write it more specifically. I'm going to give names to all the states. So here's my original NFA. I'll call them Q0, Q1, and Q2. I'm going to try and write those same arrows. We had epsilons going like this, and then an A here and a B here. All right, this was our NFA. This is the NFA, right? And this method, the subset construction, is going to produce a DFA where the states in the DFA are made up of subsets of states from the original thing. All right, so our DFA states, you know, they look like subsets of those things. So there might be one called like Q0, Q1, because that's a possible subset of states from the original machine. The original machine is Q0, Q1, Q2. And our DFA states are going to be all possible subsets of or you know, even the whole thing counts as a subset, right? Anybody remember from your discrete math class how many subsets do we expect to get if there were 3 over there? Yeah, 8 is the answer. It's in this case 2 to the power 3. It's always 2 to the power of however many things you started with. That includes the empty set, and it also includes the full set. All right. So in this case, we had 3 states to begin with, and the size of, or the number of subsets of an n element set is always 2 to the n. So the size of the DFA, it could be quite large. In this case, it could have 8 subsets. But just like in the product construction, you usually don't need all of them. So we're only going to use the ones which are reachable from the starting state. So we'll get 2 to the 3 subsets. I'll just say not all are reachable. I mean, you already know the answer is going to turn out to be this thing, right? This. We're going to end up with only 4 states. So we don't actually need all 8 of them, but you could write down all 8 of them if you wanted to. All right. So what we're going to do is we start from the starting state and just see where the arrows go. So just like in the product construction, I have to tell you how to choose the starting state. And unfortunately, it's not as simple as just Q0. Of course, there is a subset called the set containing only Q0, but actually that's not how we choose the starting state. So the starting state, I'll tell you how to do it. It's because you need to keep track of the epsilons. And you'll see the epsilons are kind of a headache in this procedure. It gets more complicated because of the epsilons. But anyway, the starting state in the subset machine is the set of all states. Let me say it's the set of the DFA starting state, which in our example is Q0. Sorry, I didn't draw that. These are accepting. Q1 and Q2 are supposed to be accepting. Although that's not going to matter for a while. Anyway, the starting state in the subset machine is the set of, first of all, the DFA starting state, together with any other states you can reach by epsilons from the starting state. All right? Because really, when you look at this NFA here, you think, yeah, Q0 is the starting state. It's true. But you can get to Q1 before you even read any of the letters. So in a sense, Q1 is also kind of like, it might as well also be a starting state, because you can get there by epsilon without even reading any letters. So when we do this construction here, we take the original starting state together with any others which we can reach by epsilons. All right? So in this particular example, where we start is, first of all, we're going to start at Q0, but also any other states which you can reach by epsilons from Q0. And that's actually everything, right? You can get to Q1 by epsilon, or you can get to Q2 by epsilon. In fact, you could get there two different ways by epsilon. So you can go that way or that way. So anyway, in our example here, our starting state, I want to pass the page break. Our starting state in the subset machine is the set Q0, Q1, Q2. All right? So that's going to be my first state in my machine here. Q0, Q1, Q2. This is the name of my state, all right? This is kind of like when we made the product machine, which was pairs of states. This is the subset machine in which every state is a subset of states from the original machine. Sorry, I had to scroll away from what I just wrote. The starting state is determined by the original DFA starting state, which in this case was Q0, together with any others which you can reach by epsilons from the starting state. Maybe I'm going to grab this picture and copy it down. Oh, isn't that great? Okay, so this is our starting state. And now, from here, we're going to draw in the arrows as necessary. And how do you draw the arrows? So for this one, first of all, there is no epsilons, because my result here is going to be a DFA, so you're never going to write epsilon transitions in this one. I need an A and a B from this state, right? How do we determine that? The A arrow from this subset is meant to go to a subset consisting of all possible states that you could reach from any one of those if you did A. So you have to imagine I'm starting in any of these states, Q0, Q1, Q2, and think about what are all the possible states you could end up in after doing an A from one of those. And you also always have to consider epsilon. So I'm going to try and write, see if you can think about that. I'm going to try and write in words what that is. I will say for each arrow, I'm going to leave some space for the diagram to fill in. We find all possible states reachable from, sorry, my handwriting, from our current subset using the appropriate letter, right? So from this state, Q0, Q1, Q2, if I want the A arrow, I have to look at the diagram and decide what are the possible states you can get to, starting from any of those three states and using an A. And I will emphasize, using the appropriate letter, possibly with epsilons. All right, so I should be looking at this diagram, starting in any of these three states. Where could I end up if I do an A and maybe some epsilons? I could do epsilon, I could do A and then epsilon, or maybe I could do epsilon first and then A, but anyway, A together with epsilons. Can you still end up anywhere? I think actually you cannot end up in any of those. You can't end up anywhere after doing an A. Maybe see one of these states you can't get to.
Oh.
Which one? I heard somebody say each of them. You cannot end up in Q0 if you do A. Like, right? If you start in any of these states here and do A, I don't know where you came from, but you're not going to end up here, right? Because actually, you can never ever end up here no matter what you do, right? The only way, this is only accessible sort of outwards, all right? So from any of these states, you can end up in Q1 if you started in Q1 and you did an A. You can also end up in Q2 by starting in Q1, doing an A and then an epsilon, all right? But nowhere can you end up in Q0. So this is a little tricky. You got to get used to this. But anyway, there's an A here, and it goes to Q1, Q2. That's because you cannot end up in Q0 if you did an A starting from any of those three states. But you can end up in a Q1 or a Q2 if you did an A, perhaps followed by epsilon. All right? Let's just keep on drawing the arrows then. So from the original state, what about B? Which states can you end up in if you start in any of those three and do B? Any thoughts? Yeah, just Q2. You cannot end up in Q0 for the same reasons as before. And also you can't end up in Q1 because the only way you can get there is by doing an A from Q1. So from here, I'll go down here with the B. Q2 is the only reachable state from there if you did B. I hope everybody's feeling good about this. It is, you have to look very carefully, and this is easy to mess up, unfortunately. But all right, let's continue. So how about from here, Q1 and Q2? So you got to look. Imagine you're in these two states, kind of at the same time or something, in some quantum superimposition of states. From either Q1 or Q2, if you do an A, where could you possibly end up after that? You could end up in Q1 if you did an A, starting from Q1. Is it possible to end up in Q2? Yeah. Yes, also it is possible because you can do A here and then epsilon. So Q1, Q2 actually goes back to itself because starting from Q1 or Q2, you can end up in either Q1 or Q2 by doing an A. What about by doing a B? Q2. I think it's only Q2 you can end up with if you do a B. Great. So B goes down like that. I feel good about that. Then we just need outgoing arrows from the bottom state there, Q2. Outgoing arrows from Q2. If I am, this is a little easier maybe just to think about one state at a time. If I am in state Q2 and I do A, where can they end up? The answer, yes, is some people are shaking their heads. You cannot end up anywhere. How would I indicate that down here? Is that Yeah, actually, there is a convenient way to do that. Every state down here is meant to represent a set, right? A subset, and this represents the empty set. A. What I'm writing there, what that arrow means is, if you start in Q2, you cannot arrive anywhere by doing an A. So that's why you should put the empty set there. That's the set of nothing. And what about state Q2? If you do B, you can end up in Q2, and that's it. So there's a looped edge like that. All right? And that's, no, we still need more arrows from here, right? This is supposed to be a DFA. Every state needs 2 outgoing arrows, although these ones are very easy, and it always goes this way. If I'm in no states at all and I do an A, where can you end up? Still in no states at all. So this will always be the case. The empty set state in the subset machine always gets a looped edge with A and B. This always represents a permanent rejection state. All right? Starting in no states at all, you end up in no states at all. All right? Check it out. That picture, if you ignore the names of all the states, it really is the same as this one. Although we should talk about how to determine which are accepting and rejecting. This is not hard to do. The way, I just have to tell you, a state down here is accepting whenever it contains one of the original accepting states. So in this example, anything with a Q1 or a Q2 in it is going to be accepting. And that gives me this one is accepting, this one is accepting, this one is accepting, and the empty set is actually never accepting because it doesn't contain any accepting states from the original DFA. So I'm just going to write in words what I just said. How to find the accepting states? Come on. The accepting states are any subsets containing original NFA accepting states. In that example, they were Q1 and Q2. All right. This is appropriate, the way you think of an NFA and whether the NFA accepts a word or not. Remember, the rule is, I said word, I meant string. Sometimes I say word when I mean string. The rule is, a string is accepted, it means one of those places where it ends up is an accepting state, right? It could end up in many places, because that's how an NFA works. But one of the possible places that it ends up is an accepting state. So that's why you want to choose any of these subsets which contain one of the original accepting states. All right? And I hope you believe me that this, if you look back in your notes, you'll see that DFA really is exactly the same DFA that I wrote at the beginning, just without the labels on it. All right? Any questions about that? I wanted to do one more example of these, and then I had one for you all to try out. Yeah.
So when you're explaining before we kind of got in this example with the 2 to the n,
Yeah.
can you just explain that again? I don't know.
Sure. Yeah. This. So in general, if you have n elements, and I'll just a little aside here. A set of n elements. Come on. This is a true fact, has 2 to the n possible subsets. For instance, if my set is, say, A, B, C, having 3 elements, there will be 8 possible subsets. And they are, 8's not so much, right? I can write them down. There's that. Those 4, and then there's also some with 2 elements. B, C, and then there's some with 3 elements, A, B, C, right? And that's it, there are 8. So in the worst case scenario, if you start with an NFA that has n states, you might end up needing 2 to the n states in the DFA, which could actually be very many. But in practice, I'm not going to make you do an example which ends up with very many. In practice, you start with the starting state and see where it goes. And hopefully you don't have to use all of them.
So like with the example we just did, right, there were 8 possible states, but we only used 4.
Yeah, that's right. Most of them were unreachable from the start. Yeah. And you shouldn't, I would not suggest you try to write down all 8 of them to begin with. You just go from where you start and see which ones you need. Yeah. Great. Okay. Yes, I got one more example, and then I want you guys to try one. How about I'm going to call these ones S, T, and U. And let's say it's like this. This one has no epsilons, which makes it quite a bit easier, I think. The epsilons make it hard to judge sometimes. You gotta look carefully. You still have to look carefully in this one. All right, this is my NFA. This one actually accepts, it's not necessary that you know what the language is, but the language of this NFA is all strings that have A as the second to last letter. The way that I think of this is, you can start off and do whatever you want for a while. Eventually, in order to get accepted, you need an A and then one other thing. So that other thing could be anything. So the second to last letter has to be an A. But like I said, you don't need to even think about that at all. Let's make an equivalent DFA. All right. Anybody remember how to do this? Can someone say, what should the starting state be? Remember, the starting state is the set of all states that you can reach from the original starting state by doing epsilons. Yeah? Yeah, just S. You always include the original starting state plus any additional ones that you can reach by epsilons. There are no epsilons in this one, so that makes it easy. I'm going to write the set containing S. Not so important. That's just the name of the state. So, really you can call the states whatever you want, but it represents a set of a single element, a subset. Okay, let's draw the arrows then. The A arrow from the set of S. You want to consider what are all possible states I can reach by doing an A from here? What do you say? Yeah?
S, T, and U.
S, and I think it's just S and T. So you think of, from here, if I do a single A, where can I end up? And you can't make it all the way to U by doing a single A from here, right? So this will be S and T. All right. And how about the B arrow from S? If you do B, where can you end up? Yeah, just S. So that means my B arrow goes like this. Okay. S and T now. So now we have to think about if you're in either of these two states, S and T. Let's do the A arrow. If I do an A from either of these, where can we end up? I think that would be STU, right? You can end up in S by doing this. You can end up in T by going across from S to T, and you can end up in U by going across from T to U. So I'm going to put this one. I did this at a time, so I know where to draw them to avoid crossing the arrows. Because you know I hate crossing the arrows. All right? Some kind of animal if you cross the arrows unnecessarily. S and T then. If you do a B, where could we end up? Yeah, S and U. Actually, from S and T, you cannot end up in T again by doing a B, but you can end up in S and U. So I'm going to put that one down here. It turns out, actually, these are the only 4 states. If you do it right, it's not, none of the others are reachable. Okay, what about, let's draw arrows from STU here. If I do A from STU, I can still get to S, I can still get to T, and I can still get to U. So I think this is one of those. From STU doing A, you can get to any of those states. What about from STU doing a B? Yeah, that would be only S and U. You can't get to T. So that's one of those. Question, yeah?
For STU,
Mhm.
from how would you get back to T if you did an A?
You can start in S and go to T.
Oh, go to T. Okay.
Yeah. Yeah, there's a lot of, you got to look really carefully when you're doing these. And unfortunately, since we're only drawing the reachable states, if you mess this up and went over to like, T comma U, you would have created a whole new branch of the diagram, which actually doesn't exist at all in my picture. So you got to get it right. All right, we need arrows from S and U, and that should do it. So from S and U, if I do A, I could get back to S, I could go to T, and I think that's it, right? So that would be just S and T, like that. Yes?
So it wouldn't do anything starting at U, since in the NFA there are no arrows in A, right?
Yeah, right. Yeah, starting, if you imagine starting in U, you just can't get anywhere from there. And then from SU with a B, S can go back to itself. I think that's it, actually. You can only get to S, starting in S or U and doing a B, so it's like that. And there we filled in all the arrows. One more thing to do is to say which are accepting. What do you say? STU and SU. Anything which has a U in it. So this one is accepting, and this one is accepting. Great. It's not so hard, I find very easy to make a little mistake, which kind of screws up the whole thing. If you mess it up early, you will.
Can you explain again what SUA is to STU?
Why? Sorry. This one? Yeah, from S and U, you can get to T or S, but you can't get to U anymore from just S and U. Yeah, all right, I got one for you all. I will walk around and see how you're doing. Let's try. I'm going to write Q1, Q2, Q3. Actually, this one has 5 states to begin with, which means in theory you could get 2 to the 5 possible states in your answer, which is 32. But in fact, actually, this one, if you do it right, has only 3 reachable states in the subset machine. I said only 3. So it's going to be trying to cut you a break there. The arrows are, here's a A, B, here's a A, sorry. That's a B there, followed by A, and then I have an epsilon, and then a V. This is accepting, this is accepting. All right. See if you can do it. Let's let's all together decide what is the starting state. If you get the starting state wrong, you're totally screwed because you will end up doing a whole bunch of nonsense that has nothing to do with the right answer. What do you think? Yeah? Q1 and Q4, I agree. It is the original starting state together with anything reachable by epsilons from there. So that's Q1 and Q4. Great. All right, see what else you think. Actually, can we draw the A arrow from there? Just for fun?
Q1.
I heard a lot of people say Q1. It's actually not quite right. It is Q1 and Q4. Yeah, how do you get to Q4? I don't know who said that.
Oh.
Yeah, because you can do the epsilon. So from Q1 and Q4, you can, in Q1, do A and get back to Q1, or you can do that A followed by epsilon and you can get to Q4. This is it. You got to be careful with those epsilons. Anyway, that means there's an A arrow like that. See what you think. I will walk around and see how you're doing.
Q1, Q2, Q4, Q5.
Yeah, it's all one.
Wait.
Just Q5, Q3 is not in.
Yeah, it's because
Everything but Q3.
this is
Okay.
where can we possibly arrive starting any of those? You can arrive at it.
I don't like how this one has four kids. I feel like
Okay.
I hate how it stayed at once.
it's like, dude, what's going on? Like, it's definitely a subset, right? I don't know. Let's see, let's do it. So B, Q1, B, Q2, you do epsilon. Q4. And then get another B. Wait, is it count them? Wait, what if you just do epsilon? I keep bringing Q4, and the B would go 5, so it's Q4.
You can do both on the spot. You can do Q4.
You're only doing one B.
Oh, one.
Yeah, you get
Why are we doing B before I go to find B? I'll
Go
go
to
B.
B later.
Yes, it's because you can from Q1
Oh, yeah, I
If
think.
you do epsilon, it goes to Q4, and then B that goes to Q5.
Yeah.
But it can also stay in Q1 or go to Q2.
Yeah.
And also stick in that.
No.
Okay, so from the big one, so
A.
if you do A,
Stay in Q1.
stay in Q1.
Yes. Q3.
You can do Q1, Q4 as well.
Okay.
Yep.
Yeah, that's good.
Three.
Oh,
With A, you just total. You can, you don't wait with Q2. You can go to Q3.
Yeah, okay.
So we have Q3, Q4,
Should be
Oh, yeah, just 3A.
that's the same. I think there should be three states. Alright. It's very hard to tell.
B from here. Q1, start to Q1, Q4, Q5, B, Q5, yeah, Q5, Q1, Q2.
It's the same. I think B is.
It's all these.
You get to like force.
Okay.
It's like force.
I don't know.
From the Q4 to Q1.
Going from here, let's be from Q1 is Q1. And then to Q2.
Q1, what's that?
Put it this way.
Q1, Q4.
Q1, Q3,
Good? Yeah.
Yeah, it is.
But there's no arrow on it.
You alright?
No, A.
Yeah.
Are you double checking?
Yeah.
So A would work because
Yeah,
A is
yeah.
epsilon.
that.
Oh, those are just-
Oh, shit. You take,
Okay.
we go from Q2 to A.
So this, so this.
Oh, you're on this.
Because
Yeah.
Q1 could do B.
Okay, so.
Yes, and actually.
This one.
Okay, that one.
Yeah.
Q4, Q1, Q3.
Yeah.
Doing it A, we have Q1, so you could go to Q4.
Yep.
Yeah.
So Q1.
I'm good.
A goes back.
Yeah, yeah.
Let's see, so this is my use case.
Yeah.
We're good.
Okay.
B, we're seeing Q1, Q4, Q3. Besides Q4, Q1.
Yeah. That's the one where you should take.
Well, I think it just goes back to the second, to this one.
Yeah.
They want to say about this, what's the acceptance?
Yeah. I still feel like it's kind of wrong.
The last one is the acceptance.
I don't because I deeply hate walking through college. Coming up here 3 times a week is terrible. If I have a time, it's gonna take my butt. Because the homework.
Yeah, that's good. But then that should be Q cross R.
Oh, it's the same as the 15%.
I did it too hard.
Yeah, yeah.
Delta is the same. Well, actually, this delta is the same as all they ask you is question. All they ask you is what is the so you need. All right, let's chat about this one. It's a little tricky. You got to look very carefully, but I think, I mean, as I was going around, it looked like people were doing great. From there, doing a B, you can get to any of Q1, Q2, Q4, Q5. All right. You can get to Q1 from Q1 by just doing B. You can get to Q2 by doing this B. You can get to Q4 by doing B followed by epsilon. And you can get to Q5 by doing epsilon followed by B. All right? I think everybody eventually got that, but it's a little tricky. From Q1, Q2, Q4, Q5, doing B is this. At least that's what I wrote on my paper. You can get to any one of those again by doing a B from any one of those. You cannot make it to Q3 by ever doing a B from anywhere, right? The only way you're getting there is by doing an A. And then from here, the arrow with an A on it goes to another state. So from any one of these, that's these 4 states here. Doing an A, where can you end up? Well, you can end up back in Q1. You could do A followed by epsilon to end up here, or you could do this A and end up there. So I believe it's 1, 4, and 3. I might as well write them in order. Q1, Q3, Q4. That was A. I hope that's what folks got. Any questions about that? All right. And then if I do from that state down there, we just need 2 outgoing arrows. 1, 3, and 4. If we do an A, the 1 can come back to itself with an A, or it could go A followed by epsilon and get to the 4. The 3 doesn't go anywhere with the A, so I think actually you can only get to Q1 and Q4 by doing A from down here. So that's this. And then with a B, 1, 3, and 4, I can do a B to get back to 1. I can do a B to get over to 2. I can go to B followed by epsilon to get here, or epsilon followed by B. So that goes back to the big state. All right, and I think that's it. Any thoughts? All right. Which ones are accepting? Anything that includes a Q3 or a Q5. So that would be this one, which has a Q5 in it, and this one, which has a Q3 in it. Those are 2 acceptings. All right, this is the general purpose method to turn a NFA into a DFA. Yes?
Does it always work?
It always works. Yeah, I mean, what could go wrong? Am I right? Yeah, actually, next time I'm gonna try and be a little more convincing than am I right? In convincing you that this really does work in all cases. But yeah, it really does. I mean, I would say, like I just told you how to draw the states and how to draw the arrows. You might say, like, what could go wrong? Maybe it wouldn't be a DFA anymore. Maybe you get like infinitely many states here. You keep on just generating new states, but that's not possible because at most there's going to be 2 to the n states, which you can't go on forever. We got 3 minutes left. I don't think I want to get into the details right now, so maybe we'll leave it at that. Next time we'll do a little proof about why this always is going to work.